Did you have any other plans for the meeting, or is it just going to be me going over stuff?
No, I have LT Spice that we're going over, where they're talking about varied resistors and how to actually set up a step param. And we have another simple circuit for simulation, and that's pretty much our meeting today.
Okay, let's go through that first. But I guess I can just introduce myself. So my name is Kyle. I was the project co-founder and project manager for the first 2 years, from 2017 to 2019, and now I'm graduated. Yeah, so you can go ahead, do your presentation on LT Spice, and then if we have any extra time afterwards, then I can try to clarify some things.
Sure, definitely. All right, so I'm going to share my screen, and I'm going to start off with my very first circuit. Let me see. All right, Daisy. Since Sunny and I have already really done it, I need you to get your LT Spice up, and I'm going to have you construct the circuit, okay? And I'll walk you through specific things that you need, but right now you just need a source, a voltage source or a DC source, a resistor, and another resistor. When we set this up, we have to set up this value as a variable, and you do that with curly braces. And then we just set these up as generic things. Normally your stuff is going to be 5 volts or 3 volts. We just chose 5 volts, and we just chose 1K on this one. And actually, this came from an old lab, and we thought it'd be cool to just show you guys how to actually do it. And then we're going to run a simulation on it. So go ahead and let me know when you get to. Actually, I'll just show you because it might take you a little bit. One of the more important steps right here that we need is a step param. We go up here at .amp. I talked about this in one of the other meetings. But up here, this is how you set up your parameters. If you already had one that was preset that was given to you for like a specific component, you'd copy and paste that in here. But if you don't, we can set up that parameter ourselves. So we do .step space param. So you're setting up the parameter. You set up your variable, which is going to be the R, your smallest value, your largest value, and then how many steps you want it to take to get there. So in this case, we're saying we're going to start at 1, we're going to end at 10,000, or at least a value close to that. And then we're going to increase the value of the resistor by 1,000 each time. So it's going to go 1, 1,001, 2,001, and so on until it gets to that point where it's going to see 9,001, and it's going to attempt to do 10,001, but it can't do that because it's not within the parameters. So that's how you set it up. You hit OK, and you just drop it off. Let me just get rid of that. Did that make sense to you, Daisy?
Yeah. Wait, which was the tab to get to start typing again? The
.op.
.op? Okay.
Yeah. And stop me if I'm going too fast, by the way. I don't mean to go too fast. Kyle, if you'd like, you could talk about what you do in industry. What do you do?
Yeah, what do I do? Well, I'm going to talk about it more probably during the open panel today.
Okay.
I joined the last open panel, but had some issues, so I had to drop
Oh
out.
yeah,
But
yeah, I remember that.
yeah, hopefully, hopefully this time no issues happen.
What was
But
it the same issue as you had today, or was it a different one?
no, that was a different like a life issue.
Oh, okay. I'm sorry to
Yeah.
hear about that. Whatever it was, I'm sorry to hear about it.
No, it was all good.
Okay.
Yeah, so basically, I'm a firmware engineer at Rivian,
Okay.
and I don't know. I think I've said this so many times that I feel like everyone should know what Rivian is now, hopefully, in the project. But for anybody that isn't familiar, we're a electric vehicle startup. We unveiled our truck and our SUV back in November 2018, and those are currently in pre-production stages right now, and we'll hopefully be releasing them, or the truck will be released in June. SUV will be released in August, and then we're also working on Amazon vans. I think those are starting to go out in September, and we'll have 100,000 of them out on the road by 2024.
Holy crap! Nice.
Yeah, so you're gonna probably see them everywhere, like literally everywhere. All the Amazon Prime vans will be converted to Rivian vans.
Do you have a feeling that it's going to be like Tesla Tesla's not strength, but like idolize how good Tesla is, or is it? You think it's more Elon Musk that's kind of like driving that craze?
Which craze?
The Tesla craze. Everyone loves Teslas.
Yeah, actually, that's pretty recent. If you go back like 4 or 5 years,
Hmm.
even, it wasn't nearly as popular as it is now. So I think right now we're kind of in like an exponential growth phase
Hmm.
for like electric vehicle market share around the world. And you're seeing that compounded by the fact that a lot of governments are introducing laws that prevent the sale of gasoline vehicles um, by certain dates. Like I think California is by 2035.
Okay.
Um, yeah, so pretty big industry to head into for anybody interested.
Interesting. Okay. And how do you like your job there? Like what actually I'll change the question. I'm pretty sure you like your job there. Uh, what do you actually do? Like, what does your job entail? If you can talk about it.
Yeah, I mean, I don't think I'll be sharing any secrets. Like, there's not too many secret things that I work on, but
Hmm.
um, I just work on a lot of networking, a lot of like operating systems for the vehicles,
Okay.
stuff like that.
Oh, I think I remember you talking, or somebody said in your place. I don't remember which. You talked about you making like libraries and stuff, right? Was that you? It might have been somebody else, actually. I'm sorry.
No, I do work on the libraries, like the platform libraries.
Okay. Okay. That's good. How's it going over there, Daisy? Have you gotten to this part yet?
How do you rotate components again?
Uh, you can rotate with Control R.
Okay.
And also as a reminder, you can mirror with Control E. Kyle, how's it feel to be out of school after being in school for so long?
It's pretty chill, honestly, depending what job you get. For tech jobs, it really depends on the week, what happens. Some weeks I'll be working like 55, 60 hours. Other weeks I'll work like 25 or 30 hours. Just depends on the workload.
Nice.
But it definitely feels good, especially making money. That's the best part.
Oh yeah. I'm looking forward to that part. I've worked so many minimum wage jobs until now. I'm like, I think it's time I start getting a salary pay of some sort.
Yeah, it's going to make a huge difference for you.
Okay. I'm not sure I did the step or the dot step part correctly.
Okay. I'll stop sharing my screen real quick. Do you mind sharing your screen?
Because I typed it and I made the .op another line, but I'm not sure if that was what I was supposed to do.
Oh yeah, no worries. If you want to share your screen, I could take a look. Also, I didn't
Yeah.
notice Jaren enter. Hello, Jaren. How are you doing?
I'm good. How about yourself?
I'm doing well. You're sneaky. When did you get in here?
I just entered like literally 2 minutes ago.
Okay.
Yeah, my bad.
Don't worry. Totally fine. We're doing step param today, so we're setting up a variable or varied resistor or potentiometer, and we're going to be trying that out today.
This is
Dot,
LT Spice, right?
yeah, LT Spice.
All right.
That dot amp, but or dot up,
Right.
comes from the simulation tool. So go ahead and delete that. Take the scissors and delete that one.
Okay.
Oh, hold up. I just realized that was the whole thing. All right, it's fine. Don't worry. Go ahead and good practice. Go ahead and just type it in again.
Okay.
I should have realized I shouldn't have put those so close together. I'm sorry about that.
Okay, step param, and then it's like R1. What was the second value?
Second value was the highest. It's going to be 10,000.
Okay.
And the last one is the number of steps that you're taking. Perfect. And you hit OK.
Okay.
Perfect. You just paste it on anywhere.
Just like that?
Just like that.
Okay.
And then for the op part, when you go to simulate, one of the top tabs,
Okay.
there you go, and drop down to edit simulation, CMD.
Okay.
Very last one, DC op PNT. On the right. There's a right tab. There you go.
Okay.
You hit OK. That's where you get your dot off.
Oh, okay.
Perfect.
And then for this, was this just because I did it like a rename resistor, or is this like a specific like potentiometer?
Just ask your question again.
So I did a resistor and I just renamed it R like potential and the R in curly brackets, or do I have to go specifically like look for
No,
it under?
no.
Okay.
That's exactly what it's supposed to be. You're good.
Okay.
Okay. Do you mind stop sharing your screen?
Yeah.
And go back to mine. Perfect. All right. Now that you've mentioned it, let's go and move this away from there. There we go. Yeah. So what we would do next is that we'd simulate it. Jaren, you don't have to do this at this junction. It'll probably be easier if you do the next set because we're going to do another circuit after this. If you want to just watch this and then watch it back on YouTube, probably be better.
Yeah, that's fine.
Okay. So we'd set up, like I mentioned, we'd go to edit simulation command. And in this case, we're going to use .op. And in doing so, we can now run the simulation. And we get some values, really nice thing. So what we're going to be doing here is we're going to be checking our current through those different steps. And to do that, something that we're doing this for in particular is what would give us our specific current that we wanted. So as soon as I click on this, we're going to see this. And we know it's linear, but it's going to look a little wonky when we have these different values that don't scale correctly with these values. But what we're going to do is after you simulate it, were you able to simulate it, Daisy, by the way, or no?
Yes, I think. But wait, the y-axis, I do that by. Wait, I don't have the y-axis.
No. Do you have a line at all? Actually, do you have that green line?
No.
Okay.
I don't have the values like the amps.
Okay. So what you're gonna do is after you simulate, it's gonna ask you what you want to check. So you're gonna take the varied resistor, you're gonna click on it, and it's gonna show you your current
Oh.
versus the resistor values. The resistor values are going to be your x-axis, and your current's going to be your y-axis.
Okay, I got it now. Thank you.
Perfect. Yeah, no problem. Something that's really cool is that you can click on this value and you can move this around. This allows you to get different information for what you want. So pretty simple. And then you have these different values here. Your vertical value being your y-axis and your horizontal being your x-axis. And we can choose specific values to match. Like we can choose a specific current that we want, and we can find out what that potentiometer is going to be, or that varied resistor is going to be. So I picked out a couple, I think. I did not. So I'm going to have you, Daisy, since you have this up now, we're going to look up 2.5 milliamps, 1.7 milliamps, and 3.4 milliamps. And I'll show you how to get the first one. Actually, I'll make another one. Let's say 2.8 milliamps to kind of show you how to do it. So after you click on the value that you're looking at, or the, what do they call it, the trace, after you click on the trace, you're going to drag this around, and I'm going to be looking for 2.8 milliamps. So in the bottom right hand corner, you see that little window. It says vertical value. I'm going to get that as close to 2.8 as possible. Which is right about there. There we go. And that's going to tell me that I need specifically an 879 ohm resistor. If you put that into the circuit, you could actually find that value. Or you can, since it's such a simple circuit in the first place, you could just use, sorry about that. You can combine your circuits or your resistors in series and just Ohm's law that value out. Does that make sense to you, Daisy?
Okay, so I just have to find the one that's the closest and then do the Ohm's law to get it.
No. In this case, the right value is with the current that we want. The left value is the resistor value that we're looking at.
Oh, okay.
So in this case, this resistor would be 879 ohms. Okay.
Okay.
All right. And then if you get a chance, go ahead and I'll actually leave this for you guys to try at home. So when Jaron gets a moment to set up his circuit at a later date, I'm going to have you guys find these values and report back to me next Sunday. Not next Sunday. Actually, it might be next Sunday. I'll have to figure out, depending on when everyone's available, if we're having another meeting next Sunday or the following Sunday, okay?
Wait, what values do you want us to find?
Go ahead and find 2.5 milliamps, 1.7 milliamps, and 3.4 milliamps.
Okay, cool. And you want us to find R pot for those different amps?
Yeah.
Currents. All right, cool.
Pretty simple one. Okay. And then we're going to close this one down. And I'll wait for at least Daisy. Were you able to confirm the first one being the 879 or whatever it was?
Yeah, I got it close to like 870.
Perfect. Okay. So close this or open up a new one. And we're going to set up this circuit next. And this one's going to take a little while. So Kyle, if you want to talk about anything, feel free, hop in.
Yeah, I don't have much to say.
Okay. No worries. Just want to make sure I wasn't like keeping you quiet for any reason. Just feel free if you want to talk about anything.
This is a good refresher on LT Spice, even though I'll probably never use it again.
How dare you? It makes sense if you're doing like programming and stuff, but I don't know. I've noticed a lot of people will put it on their resumes and stuff. They'll put LT Spice or P Spice because it's helpful if they're actually building circuits.
Yeah. In the real world, I don't think it's too helpful unless you're actually doing like a hardcore hardware engineering design where like all the tolerances have to be perfect and you need like guarantees that it's going to work.
Yeah.
But generally, if you have a bunch of components in a circuit, usually each component will have their nominal power output and like current draw and all that. And you typically just add those up, call it a day.
Yeah.
But if you're going to any sort of research, then this is helpful.
Yeah, I agree with that.
I will say that this program looks, I don't know, I've always thought it looks like it's out of the 90s. It looks pretty old.
Yeah.
I've seen worse, definitely, but I think Altium and also I think Autodesk has an offering too. Like there are better schematic software programs out there, but of course you have to pay for them.
Can you repeat those names again? You said Auto what?
Autodesk is a company. They make a whole suite of software, like CAD software, which I think I might have you guys use for making a new schematic. Debatable. We'll talk about that later. But the other one is Altium, which is like the industry standard for, all things like schematics, hardware design, electrical design, even like 3D modeling. Altium has a lot of different things. Simulations.
Okay. All right, and how's it going for you two with the schematic?
I'm finishing up right now.
Okay. Whoa. All right, go ahead and just let me know when you both finish up and we can start editing the simulation command.
This is very similar to what you would do in like EE1A, right?
This is from 1A.
Okay.
This is one of the labs that they had. But I remember in 1A you only use PSpice, I think, in one lab, and I think you could probably do it on some of the homework problems, but like, or sorry, no, I'm thinking about MATLAB. They did that in the same lab. Yeah, I don't remember using PSpice too much until 1B, and then from then on, everything's been PSpice. Or in this class, for some reason, they chose LT Spice for 100B. which I find interesting. And I noticed that after getting into 100B, people in 100 or sorry, in 1A are starting to tell me that they use LT Spice. So I'm like, it's probably a better idea that I can get some practice with this. And if the next group of students that are coming in are using LT Spice instead of P Spice, it's probably better just to use this.
Okay, I'm done with the circuit now.
Perfect. So then we're going to go to edit simulation command.
Yeah, I'm done building as well. My bad.
No worries. We're just going to do transient this time, and we're going to set a time. And the stop time is basically after how many seconds are we going to get information about it. So you can do 100 seconds, and usually you do this for like, I found it easier for AC stuff where you could actually see like a sine wave, stuff like that. But we're just going to use this one anyway. So you do that, you paste that .tran1 anywhere you want, doesn't matter. And then we're going to set up the simulation. So go and let me know when you get past that edit simulation command.
What were the values again? The stop time?
Oh, just 1 second. You just put 1.
Is it just 1 and then that's it?
That's it.
Okay.
Yeah, it knows to put seconds, and you would just edit it for however long you want it to be.
All right, I click. You want us to simulate it, right? Just simulate, then run it.
Yeah.
Oh yeah, I just did that.
Perfect. So once you get here, we're checking different current values. Ooh, I need to switch those. So when you hover over the resistors, actually I'll make this a little bit bigger. You hover over the resistors, they actually have orientation in LT Spice. So if you notice, this current's going backwards. And I would just need to pick these up and rotate them. So I'm going to actually do that real quick. And as a reminder to rotate, it is Control R.
Sorry, why are we rotating them? Aren't resistors nonpolar?
In LT Spice, they have polarity.
Oh.
I'll show you that in a moment. Let's go and simulate it again. Now you can see that it rotates a different, or it goes in a different direction than the current. So this is something to keep an eye out on. If you'd done the last one with the resistor in the wrong direction, it'll just be like you just have like a negative current that you're just working with, but it's the same thing. Like it's just a flip value. So anyway, this one you guys could just play with yourself. Basically, you can check all the currents inside this thing. You could check nodal voltage by just clicking in random areas, and then you can actually click on it to find what it is. You could also find, just run this again. You can find each of the currents that are in here, and those values will be on the right hand side. So yeah, I just wanted to bring that up. If you have any questions about this, please let me know, or message me in Discord or email me. But that's just the rundown. Feel free to make your own circuits to practice. Sometimes, depending on my homework, sometimes I'll do it to double check my answers. if I have time to do it.
No, yeah, that sounds good.
Sounds good. Okay. Kyle, I have nothing else. I just wanted to bring up these couple of things. Feel free. We can talk about what we're going to be doing pretty much. You said we're going to be revising again that schematic, or are you just going to talk about the schematic?
Well, right now we're not going to be revising it, but it does need revision, and that's up to you guys to figure out. But I guess I just wanted to point you in the right direction for that.
Okay.
So I'm going to start sharing my screen.
Sure. Let me go get some paper so I can jot some of this down.
Okay. So this is actually the first time I've looked at the team drive.
Ever or in a while?
I think ever, or maybe I looked at it once or twice before. But
top right is schematics.
Yes. So I was looking at this folder, and there were these files here, like the schematic files.
Yeah.
And for some reason, they didn't have the extension on them, so you couldn't open them up.
Yeah.
I don't know if you noticed that before.
I noticed that that the schematics, they had a revision A and a revision B, so I just went with the latest one, but the others I didn't even try looking in yet.
Yeah, so this revision B is the latest one. Unfortunately, I don't think anybody's touched it since I made it like 3 years ago. So
okay.
I mean, I just made a change, but that doesn't count. So the biggest thing, or the only things that changed were, actually, let me pull them up side by side. I already have it open here. So we have revision A here. If you'll notice, the solar array, this was assuming that we would have one bypass diode per every 3 photovoltaic cells, and this is not the case. It also says we have one MPPT, but we actually have 2. So that's why revision B now has these 2 blocks and very nondescript. Like, we should fill this out probably with the final configuration.
Okay.
So what happened with the solar? I should probably be telling this to the solar array lead, but when we got the solar cells encapsulated, I don't know if you guys have seen pictures of them, but they come in like modules or sheets, and each sheet has a shape that we laid out in a picture somewhere.
I think I remember seeing the picture.
Yeah. Okay. I don't know where to find it, but we should take each of those, and I think we have to come up with the wiring for the vehicle. So first of all, we have to wire each sheet together. Second of all, we have to figure out where to place each bypass diode. And the bypass diodes go in between the sheets. However, our sheets are center tapped, which means typically you would only have 2 terminals for each sheet. You would have a positive and a negative terminal, and the rest of the cells you would not be able to access because it's under the encapsulation. But our manufacturer, they center tapped it, which gives us an extra place to put a bypass diode. So say we have a sheet of like 18 PV cells. With a center tap, we can put 2 bypass diodes on that sheet. So 1 for every 9 cells. But without that center tap, we would only be able to put 1 per every like 18 cells. So that's the benefit of having those center taps. Now I know everyone's like quarantined, and so you probably haven't seen the solar sheets in person, but it's really cool. Like you guys should take a look at it when you get the chance. But actually, on the other hand, they're super fragile. Like they can crack with the slightest bend. So it's probably also best to handle it very carefully and probably not take it out of the casing unless you really need to.
What are you guys designing these schematics on?
This is draw.io.
Oh, okay.
So yeah, this is a super useful tool. You got like basic shapes here, but then you also have all these really good categories. So for instance, UML. If you have taken a UML class or a class where you learned UML, it'll have like classes, and you can define software this way. Software
Okay.
or like components. Also state machines. Besides that, there's an electronic section. I don't know where it is. Flowcharts. No, I think, oh, you probably have to like download it here, but there's a really helpful electric section. That's where I got all these things from. Wait, where did that come from?
No idea. It's
I
interesting.
think I accidentally clicked something. Yeah, that's where all these components come from, like the relay, the switches.
Did the BMS come from that as well, or did you have to upload that image?
This isn't an image. This is like individual pieces.
Oh, and you actually just squared it off. Okay.
Yeah, I spent quite a long time on that.
So you said the solar array is the only thing that needs to be revised on this schematic, or?
No, so I'm just going over what changed.
Oh, okay.
So another big thing changed is the battery voltage.
Okay.
So you'll see we actually changed our battery configuration, I think 2019. And the reason we did that was just to, I think the higher voltage you have, the more efficient the motor will be. That's why Tesla now is using, shoot, I forgot. I think like 860 volt buses, like high voltage bus. Whereas Rivian right now we're using, oh man, I can't remember the number, but it's like 360 or 400 volts. So yeah.
Were you able to meet with Adrian yet, the battery lead?
No.
Okay.
Yeah, basically you only met with
Nathaniel for sure.
Yeah. And there's a reason for that. The reason is most of this is already done. I mean, not too much design work has to be done. And we actually have almost all the parts already. So, but the driver interface has a lot to be done. So I was kind of worried about that.
Okay.
Okay, another thing that happened was this block here. So it should really be like a block. All these components are on the fan controller board that we designed and we printed out and assembled. So I think we have 3 of them just in case like one gets blown or something.
Okay. Can you do me a favor? I don't recognize that specific diode that's attached to that MOSFET. What is that diode?
Oh, so this one?
Yeah, what is that?
This is a Zener diode. It's not actually like a separate diode. It's just the base. You can just think of it as the base of the MOSFET.
Okay. Interesting. Okay.
Yeah, there's I really can't remember. It's been a while, but I didn't put this, or did I? Maybe I did.
Do you know what class teaches that?
class.
Yeah, if you can
I'm
remember off
not
the top of your head.
I'm not too. So I was computer engineering. I didn't take that many electrical
Oh,
classes.
okay.
I think 100A and 100B teach that. 100A.
They teach MOSFETs for sure,
Yeah.
but they don't teach you like. Actually, now it's coming back to me. I think this is called a flyback diode or a flywheel diode.
Back or flywheel. I'll take a look.
Yeah, and the purpose of this is during the time that it switches on to off, this
Mhm.
will be disconnected, and there will be like a leftover voltage across the MOSFET. And the purpose of this diode is just to, like, the current will just go like this and dissipate.
Okay.
Yeah. It's just to protect the MOSFET. And mostly you'll see it in motor controller designs. They implement some of this.
Okay.
Yep. So this is the other thing that changed, the motor or fan controller. And then one more thing. Is there one more thing? That might be it, actually. I think that's it. So what I was going to suggest is, I know there's a lot of like aspiring engineers here who might not know what each of these things are. For instance, like, what is a relay? Like, what's a flasher relay? How does this circuit work?
Hmm.
What's a diode? How does that work? What's a fuse? How do you choose which fuse to use? And just basic like components on the schematic. I think you guys should spend a while like creating a document that maybe links reference pages online to like show, or just so people can learn exactly what each of these components do.
Sounds good. That's actually a really good idea.
Okay. I know there's more I was going to talk about. Okay, so these are like nondescript, right? It's just a block, just positive and negative, but that's not actually how a DC-DC converter is. I think this is because we haven't chosen this yet. So you guys might need to choose this. You might need to choose this. And once you choose it, you need to see how when I made the motor controller, these are the pin numbers. That's exactly what you have to do for this and this. And that's what should be done for Arduino, Uno, and what else? And the MPPT especially. We got to make this schematic. Maybe you can create a Rev C for this year. We got to make it like more finalized.
Okay. Actually, I did have a quick question for you. Why is that line red?
This is the high voltage bus. So this whole line is 115 volts.
Perfect. Thank you.
And do you know what this is? Pre-charge relay.
No, I don't think we've covered relays in my classes yet, but I plan on looking these up anyway for the documentation anyway. If you want to talk about it, you totally can.
Yeah, so a relay is just a switch. It's a way to physically isolate one circuit from another for safety reasons. So you can control like a really high voltage bus like this, 115 volt. You can control this and have it completely physically isolated from this low voltage line. This low voltage line is I don't know, probably 5 or 12 volts or something. and it controls this switch, which turns on, closes this switch to turn on this line.
Okay.
So in essence, like a relay is just a switch. Just think of it as a switch.
That's controlled pretty much, like a controlled switch.
Yeah, it usually has like, well, there are a ton of different complicated relays out there, but these are the most basic form. You just have like a positive negative on the power line, and then a positive negative on the control part of it.
Okay.
And this precharge relay, this is called a precharge resistor. Should probably put that. So this is specific to pretty much motors or any really high load, high current circuits. And how do I explain? So say I don't have this. Say we don't have that. Now we have this positive here. Okay, the car is off, vehicle's off, this contactor is closed. Oh, and by the way, contactor is just a relay, but like really, really high voltage, meant for like cars and stuff. So the switches are open right now. So this line would be 115 volt, whereas this line would be 0 volt, right? Because it would be connected to ground. What happens when this switch closes? Now we have a short here. So this 115 volts is connected directly to the motor controller and also the MPPT and whatever else we have driving our circuit. And in those short few milliseconds, the current will spike. It'll be like, well, you don't know what it'll be, but it's just like well, I'm really bad explaining this, but it would help if I had a graph, but the graph would look like if time is on the x-axis, current is on the y-axis, then it would look like this. It was like decrease over time.
Exponentially, or
like very exponentially. It'll start like way up here, and then within like a few milliseconds, it'll drop down to like a reasonable amount.
Okay.
So what we want to prevent is that spark, that spike of current, because that will probably blow this fuse. And to do that, we just add this precharge resistor. This will limit the current flow until our load, which is our motor, charges up enough. Like the, I don't know, the latent capacity gets charged up.
Okay.
So yeah, that's all the precharge resistor does. Something to note is I just took this off of like a hobbyist electric vehicle schematic that I found online.
Mm-hmm.
So I don't know if this is the right value we need. I'm sure it's probably good enough.
I'll take a look. Precharge resistor value.
It's really hard to find information online. This is like specific like automotive engineering stuff that I'm not really familiar with.
No worries. I might be able to find somebody that knows this information. I'll try that.
But yeah, when in doubt, when you build the vehicle, just connect like a, what is it called? A amp meter in here, and just measure the current that goes through. Right when you turn it on, you want to measure that instantaneous current.
Okay.
what current would be too high? Like,
So we have a 70. This is what our system is rated for. 70 amps. I believe our motor is like 50 amps. I'm not too sure on that. The number's somewhere. But oh well, we have a 50 amp circuit breaker here anyway. But this is only just to protect this fuse from blowing up. And this fuse is a fast-acting fuse. It's required by the ASC challenge to, to have a fast-acting fuse. It has to respond within a certain amount of time. And the fuse I chose, I'm pretty sure it responds in like the tens of milliseconds range. So as soon as like more than 70 amps goes through this fuse for like tens of milliseconds, then it'll break. And contrast that with like a slow acting fuse, maybe you can have like a lot of transients if your power signal looks something like this, and a lot of times it goes above 70 amps, you would probably want a slower acting fuse so that it wouldn't like break immediately. Yeah, those are the big things. This one we call the supplemental battery. It's just going to power the BMS basically.
Yeah, I think I've seen the BMS already. I remember it having like fans and stuff like that. Is it to mainly like, power the fans, or is it to power something else?
It's to power the BMS because these coils control these contactors, which isolate the battery pack. So once we turn off the battery pack, if we only had one battery, if we only had this battery, we wouldn't be able to turn the system back on because the BMS wouldn't be powered. So that's why you have like a secondary battery. In the industry, this is called an ignition battery, even for electric vehicles, which is kind of ironic. I don't know if they still call it that, but you can think of it as the battery that helps you start your car up.
It's all very good information. Thank you.
Yeah.
Are you coming through for the lost bits?
For the lost bits?
Yeah, the lost bits. It looks like you're like, all right, is there anything else before they call me?
Yeah, so the schematic and also this one, these were all me. So if you have any questions on these, I can answer them. And probably nobody or very few other people will know what's going on, unfortunately. And that should probably change. This is also out of date, by the way, because notice we were planning on using a STM32 for telemetry, and we ended up going with the Arduino. And there's also no driver interface on here either, which I think is probably going to be powered by that.
So you helped design the schematic last year, or
No, this was like 3 years ago. This was the first year of Solar Car that we designed a schematic.
Okay.
Yeah, because the plan was, when we founded the project, we were going to build the car all in 1 year and compete like the next summer. So we did like a huge amount of design work and tried to get all out of the way. What we didn't realize was building the vehicle was actually way harder than designing it for some reason. And that's really what the challenge has been the past 2 years.
All right, Kyle, it looks like we should get to the point where we wrap up this meeting.
Yep, sounds good.
If there's anything else you want to talk about, please feel free to. We were going to see you today at the general meeting, right? You said?
Yeah.
Okay. So if possible, we can save any more extra questions from then if there's time in there. Kyle, you free to let them contact you, or do you want me to have them contact me to contact you?
I mean, any questions, just hit me up on Discord. I will say though that I don't get notifications on Discord for some reason, so I might take a while to respond.
No worries.
Yeah, just hit me up on Discord. My username's Kyle or something like that.
I'll look into that myself. I have do not disturb on me. That's why I don't hear any notifications. It might be something similar for you.
I don't know, because I get it like on my desktops and my laptops, but not on my phone.
That is
It's kind of weird.
interesting.
I think iOS in general has problems with notifications sometimes, because Slack used to have a ton of problems with the notifications on iOS.
Okay.
And I think they fixed it, but I guess Discord did not fix theirs yet. So
Okay. Well, everyone, you are free to go. Again, if you have any questions for me or Kyle, message us, and we'll see you all at the general meeting today. Y'all have
What
a
time
great
is the
time until
meeting?
then.
The general meeting?
Let's look it up there real quick. Where's my
'Cause I did
spreadsheet?
not see it.
No worries. Normally I think it's like 2, but let me give you a defined answer because I have it on my schedule, which I have to find. Sunny, do you happen to remember off the top of your head? All right, no worries.
I found it. It's 2 p.m.
2, okay.
Yeah, all right. Cool.
Okay. Well, I'll see you all there.
I'll see you.
Until then, have a great time.
Yeah, you too.
And thank you again, Kyle, for helping us out.
yep, no problem. Thanks everyone.
Definitely.